Good evening, ladies and gentlemen. Tonight we're going to discuss hydrostatic pressure. This video is going to cover an intuitive explanation of hydrostatic pressure, the nomenclature associated with it, a derivation of the equation, as well as some application problems. So, jumping right into it, hydrostatic pressure, first and foremost, is a force over an area. And so this is unit force over unit area, typically a uniform distribution, and the hydrostatic aspect is because the weight of the fluid is causing this force, which is then applied over an area. And so here the diagram shows a little bit of water, a water column over some area for which the weight would be imparting a force. And so this doesn't have to be water, it could be any fluid. It could be something like oil, mercury, refrigerant. Really, as long as the density is given, you can resolve the hydrostatic pressure. So in your day-to-day, you've probably felt this when you were swimming. When you swim at the top of a pool, you don't feel much pressure. You are probably having fun, you're comfortable, you are enjoying the beautiful pool. But when you dive down to the bottom, you will probably feel it in your ears and all over your body. It is this increased pressure, this increased force, because there is so much water, so much weight above you, it is all pressing in on you. And so that is how you have probably felt it in some real world capacity. And the force moves linearly with depth. And notably, hydrostatic pressure is always applied normal to some surface underwater. This will be very important when we get into application problems, as you might have a slanted gate or something along those lines. So hold tight until we get to resolve that. And this matters for things such as dams, submarines, waterproofing. Really, if you're ever dealing with water, you need to keep this in mind. All right, and then something else. So point A and point B do have the same pressure. This has to be clarified. Point B here, despite the fact that it is not directly under the same water column as point A, because it's under the same height or in the same depth under the water, under the surface of the water, it has the same pressure. So do not forget that. You could get tricked up on an exam or something along those lines. And now going into notation, you will see specific gravity show up. This takes the form of gamma, and it is normalizing the density of some fluid to water. And so you may see something say, the specific gravity is 2 for this fluid, or the specific gravity is 0.5. And so it doesn't necessarily need to be above or below 1. It could be really any number. And it's just a statement about the density. Again, you need density to resolve hydrostatic pressure. Something else that you want to know is that these little triangles, I did not make these images, and so this is a universal sign. You may need to know this for hydrostatic pressure. The reverse triangle on the surface of a fluid means you are at atmospheric pressure. And so since really most of your problems should be solved in gauge pressure, which is relative to atmospheric, this means you don't need to worry about that. And I just want to point this out because you could see it and not know what it means, and then you would not know what your external pressure is. So let's get into the derivation. Here I have a fluid column within a box, and we're going to show how the weight of it applies a uniform force to some bottom surface. So here we're highlighting this. We have fluid at the top. The surface we care about is at the bottom, highlighted in pinkish red. And we're going to get right into it. So first and foremost, you have some external force. This is typically a pressure. Oftentimes it'll be atmospheric pressure, but it doesn't need to be. And then you've got the weight of the fluid. So both of those contribute to the hydrostatic pressure. So resolving the external force, it is simply coming from the pressure given. You multiply it by the area to get the force, and that area is referencing our little pinkish red area that we're trying to solve for. So, weight of the fluid. This is mass times gravity. In this case, mass is the density of the fluid times the volume. This V is the volume, which in this case is area times height. Area, again, being our little pink red guy. And this is a 2D view if you haven't already put that together. Height is just the height of the water box in this case, or height under the water. So adding these up, you get the resultant force, which we will then divide by the area to get the resultant pressure. You have F external plus weight of the fluid. And when you put them together, you'll notice when we divide by the area will cancel out. And so here we're dividing by the area to get resultant pressure, and then the areas cancel out. Here we have P resultant is equal to P external, otherwise known as P naught, plus rho GH. And with that, we will get into the application problems. Here you'll see we have an angled gate. That will be very important. And let's get into it. You are a dam engineer, and you do not want the circular gate near the bottom of the dam to open. You can apply a force to the far edge of the gate. What is the minimum force required to keep the gate from opening? Excuse me there. So before we begin, there's a few things we need to unpack. First of all, this is at atmospheric pressure, and we know that because of our little inverse triangle there. Second of all, this is not only a force problem, but a moment balance. We can tell from the diagram of the gate here that it's pinned at the bottom corner. And so if we were to do a generic force balance, then the x and y forces would balance regardless because this would equalize them. And so instead we need to do a moment balance to make sure this is not going to rotate. And that's hinted at because it's stated that we're applying a force to the far edge of the gate. If this was a normal moment balance, that information would not be given, and it would just say you can apply a force, like keep the gate from moving. But instead it's going to rotate open. So we need to prevent that. And then third of all, it does not say how far into the page it's going. And we don't need that because this is a circular gate right over here, circular. And so the diameter is 3 meters. And so we can just move on. Now, the first step in solving these problems is drawing the pressure distribution. So as I said earlier, this is normal to, the hydrostatic pressure is normal to the surfaces we're dealing with. And so it's really weird and kind of angled in this way. And as a result, there's two ways to solve this. One is you break up this geometry into a triangle and a rectangle and solve it that way. Or you use one of the more universally applicable equations. And we're going to do that because that's generally easier and smarter. And so the way I know that this is what it looks like roughly is because, this linearly increases with depth. If it were to go up, it should technically intersect up at the surface of the water, but I didn't draw this too accurately. So that's what we're dealing with. The equation that we need is the resultant force. And so I'll draw it in red so we know where it's pushing. Or, well, we don't know where it's pushing yet, but we'll do FR. And then F is what we can apply. All right, so the equation we need is FR is equal to rho G YC, that's a subscript, sine theta times area. So there's a bit to unpack here. Rho, we know this is water. G, we also know it's 9.81. YC, I'm going to need to explain. Area we can calculate because this is a circular gate. All right, so first of all, I'm going to redraw this so we can have a bit of a bigger diagram and know what we're dealing with. And this will make this a little clearer as we resolve YC. So I'm going to pick a different color. YC is the value from the centroid of this shape, which is right in the middle. So we'll say it's right in the middle. And it goes all the way up to the surface. And so if I were to draw it here, let's say the centroid comes down this way, that's in the same plane. It would go like that. And YC is always at the same angle of your shape. And so we know that this is at 60 degrees, and this is YC. This is YC as well. And so we need to solve for that. We can solve for that pretty easily. And we're going to need the height under the water that the centroid resides at. And so we can take the height. The height is always vertical. And so this will be h of c, we'll call it. And again, this is what h of c will look like. I know this is a very cluttered diagram, and so I'll try and draw it out. So if you'll pardon my disgusting handwriting, that's in the same plane as the centroid. We're gonna assume that, and then h of c is this value. All right. So that's h of c. We can get h of c. We can get y of c from h of c using the equation I'm about to write down for us. So, well, let me try and do this in the right colors. So y of c is equal to, it'll be h of c over sine theta. And so h of c, let me grab that. All right, we've got h of c. We have y of c. Well, we don't have y of c. We can calculate all of this. And so h of c, the calculation goes something like this. It'll be 3. Well, sorry, let me just try and keep the colors straight because this is going to become a very cluttered page very quickly. So this will help decipher what is going on. So it'll be 3. We get that 3 from right over here. And then it's 1 meter plus another 1.5 meters because the diameter is 3 meters of the gate at 60 degrees. So it'll be 3 plus 1 plus 1.5. And all of that is of sine theta. Or not even of sine theta. That's of sine 60. Sine, let's see if I can squeeze it in, 60. That's what that is. And so we can actually calculate that. This value comes directly out to 5.165 meters. All right, that's our h of c. And we can then plug that in to get y of c. So we will have 5.165 and it'll be all over sine of 60. And then that'll equal y of c. And then y of c finally comes out to 5.964. And then we're very happy because now we have y of c. That's probably the weirdest parameter that we need to calculate. And then we'll multiply by the area. The area, I'll calculate right over here. Area is equal to pi r squared, where r is, again, half of 3, so it's 1.5. So is equal to pi 1.5 squared, and that value comes out to 7.069 meters squared. That's what that comes out to. So with all of that, we can calculate F resultant. We can plug this all in, which I'll do all the way down here, just so we know where it's going. And so we'll get F resultant is equal to 1,000 kilograms per meter cubed times 9.81 meters per second squared times YC, which is 5.964 meters, times sine of 60. We'll try and put that in parentheses, and then if we can fit this in, 7.069 meters squared. Meters squared. So FR comes out to 358.153 kilonewtons. 358.153 kilonewtons. But that's not the answer. Because as I said, this is a moment balance. And so while we have half of the answer, we need to figure out where this force is being applied. Because if you look here, this is not simply rectangular. And so this is instead applying through the center of pressure, and we need to calculate that. So I'm going to redraw this again right over here, and we may run out of paper, so I may need to go to the next page. And I'm going to try and describe what is going on, because this is going to get complicated. So here's your centroid. We'll just call that C. And then your center of pressure we'll call P. All right? P is more down or closer to the bottom than C. Because if we look here, once you get deeper, then you have more pressure, and thus the equivalent point where you apply this force as a result of pressure is going to move lower. So we have an expression for this actually. And so let me grab another number. We'll grab orange this time. And we're going to grab a y value called ycp. And this, again, goes all the way to the surface at the angle of 60 degrees. So I'm not going to draw that out on this main guy because holy guacamole, this is cluttered. So ycp we have an expression for. Oh my gosh, I lost my color. ycp is equal to yc, which is the centroid y, plus ixc over yc times the area. And this is the moment of inertia of our gate, of the shape that we're trying to deal with. And so this may not be given. You may need to know it off the top of your hand. For a circle, it is 1/4 pi r to the 4th. So we'll just draw this over here. 1/4 pi r to the 4th. All right. And so if we calculate that, we have 1/4 pi 1.5 to the 4th. I know that's agonizing to try and read. And that value comes out to 3.976 meters to the 4th. 3.976 meters to the 4th. Okay, now we have everything we need to plug in for YCP. So, let me draw that a little lower. We'll go down here. This will probably be the last thing we can fit on this page, and after this we will be pretty close to completing. So 5.964. That's not even going to be enough room. Holy. Plus 3.976 meters to the 4th over YC, which is 5.964, times the area, which is 7.069 meters squared. So the units actually do work out. We have meters cubed on the bottom, meters fourth on the top. We're in the numerator, and that gives us normal meters. So the result is 6.0583 meters is YCP. Okay, with that, we need to move on to a new page. So we have YCP is equal to 6.0583 meters, of course. We'll make that a little more legible. And I'm again going to redraw what the heck we're dealing with. So we have YCP right now, which goes through the center of pressure. And we're going to need to do a moment balance, which means we need to know how far away from the pivot this is. So we're going to rerun and find the pivot point. And by rerun, I mean reevaluate the y at the pivot, which I'll use a new type of blue. This is not water we're talking about. And this will just be yt, we'll call it. Yt for the pivot. And we're going to need the h of t. The h of t we can get somewhat easily by, well, first of all, let me draw h of t, just so we know what we're talking about. H of t is the vertical one, and then h of t is equal to, let's switch back to our white color, 3 plus 4 sine 60, which will equal 6.464 meters. And then, if we recall our other value, sorry, let me grab blue again. Yt, our other equation I was going to say, we have yt is equal to h of t over sine theta. And we'll just plug that in and plug in our 60 degrees. And yt is equal to 7.464 meters. And then the length or the moment arm that the pressure is exerting, we'll call L, will be yt. You know, it's actually so sad that I'm now abandoning the colors for that one y. Nevertheless, yt minus ycp, that is equal to the moment arm. And so we have 7.464 meters minus 6.0583 meters. And that gives us 1.4058 meters. So that's the moment arm. Now we can do our final moment balance. So I'll draw the gate one last time, and then we're just about there. So we have y, or sorry, not even y, f, just normal f. At the edge, we have f resultant, somewhere right around here, and we know the moment lengths, the moment arms of each of these. And so this will be balanced. It'll be 0 is equal to f times 3 minus fr times 1.4058. That's meters. That's also meters. And so f is now equal to fr times 1.4058 over 3. And the meters cancel out. And our F is 167.83 kilonewtons. And that's the answer. Application problem number 2. What is the pressure at point B? What is the pressure at point C? So the relationship that this problem is trying to uncover is that when you move up in altitude within some fluid, or decrease your height, you will be decreasing your pressure, and when you go down, you will be increasing your pressure. And then we'll also discuss what happens when we go to the side, which is it does not change your pressure. Also, before I forget, and before you click away, when you're moving through air, so if you're going up in air, that is negligible because air's density is so small compared to any liquid, albeit I know air is a liquid, but like any true liquid, that it does not have a significant effect. So this section over here is truly negligible. All right, but we're getting off track. Let's go to point B and find the pressure there. So we're going to start by going to PB is equal to 70,000 pascals. And then when we go up, we will be decreasing in pressure. And so rho GH, this is specific gravity of 1, this fluid that is uncolored, which means we can just do gamma of H2O because it's always based in H2O. So it'd be 1 times gamma of H2O, but you know, we don't need a 1 times. We all know that that's just gamma. So that's the rho G, and then the H is 0.4 sine of 30. And I got that from this. So 400 millimeters turns into 0.4 meters. And then sine of 30 is 30 degrees because this is angled at 30 degrees. So we need to find the height. And this is in degrees, notably. Make sure your calculators are in degrees. So that captures that, and then the next one is another gamma H2O. And it will be times 0.2, because that's the height. All right, and so we will plug in our numbers. We will have 70,000 minus 1,000 kilograms per meter cubed times 9.81 meters per second squared. And then I'm going to factor that out because I don't want to rewrite it. 0.4 sine 30 plus 0.2. So you see I factored out the rho and the g. And then what we get is we get 66,000 pascals. Well, 66, 79.9 pascals. So that's pressure B. That's done. That's nice and simple. That was a good one to start us off with. And then pressure C will get a little more complicated, but even then it's not too bad. So pressure C, first thing we do is we're going to start off at 70 kilopascals because this is supposed to be a gauge, by the way. I may have forgotten to mention that. This is a gauge, and that's how we know where to start, right here, where the only pressure is known. Because nothing is exposed to the atmosphere, we don't have any good starting point beyond a given pressure, which is right here. So we're going to start, again, 70,000 pascals. And then we're going to go down, and that's going to increase our pressure. So we're going to do plus gamma H2O, because we're still in water, times 1 meter. And then we're going to move over, so if you'll imagine like we're following the line. So we've accomplished this so far. We can move over, and the pressure does not change. And then we're going to need to move up within water 10 millimeters. So because we're moving up, we're going to subtract gamma H2O, that's the fluid we're in, and then 0.01 meters, because that's what 10 millimeters is. And then we need to account for this new fluid with a specific gravity of 0.8. And so because we're moving up, we're going to subtract again, and so it's going to be 0.8 times gamma of H2O. And then the height is 100 millimeters, which is 0.1 meters. So we'll do times 0.1 meter. And then it's like you could imagine we've gone through this, and then we need to go through the air and move over. And we can do that without changing our pressure at all because the density is so small for air, it does not matter. So now we're going to be going back down. So we're going to be adding pressure. So this dark blue fluid is specific gravity of 2, so it's going to be 2 times gamma of H2O. Oop, what's going on there? And then the height is 120 millimeters, which is 0.12 meters. Then we're going to go down another 30 millimeters. So you can imagine that we've jumped down to there. And then because we're going down, we're going to, again, add. Holy crap, that is a bad addition sign. Add this, which is a specific gravity of 0.8, so it's going to be 0.8 gamma H2O times the height, which is 0.03 meters. And then we just need to resolve all of this because we go over here and then we move to the side and we are at point C. Again, moving to the side does not affect the pressure. So keep in mind gamma of H2O, I'm not going to rewrite all of this just to fill in gamma of H2O. Gamma of H2O, I'll write it out for us, is equal to 1,000 kilograms per meter cubed times 9.81 meters per second squared. We'll put a little time symbol. That's what it is. And so if you calculate this out, you get 81,505.4 pascals. Put a little comma there. And that's pressure of C. Very simple, very easy. And now you know how to do these problems. They're not too difficult. They're pretty straightforward. You just need to recognize it and know what to do.